Hello and welcome back. Today I am very excited to finally have something ready for showing, and what I'll be introducing is the first of two parts about generating a navigation mesh. In this video I'll cover generating a simple polygon boundary from a triangle mesh. After this I'll cover an implementation of the Ramer Douglas Peucker algorithm that will eliminate linear vertices and reduce small concavities. In part 2, I'll cover a decomposition algorithm used for breaking up the polygon into convex pieces, and closing with a pathfinding algorithm to traverse the generated NavMesh. I hope you enjoy. Before going into the actual algorithm, I think it would be beneficial to discuss the process that led to this final algorithm. My first efforts at creating an algorithm for generating a polygon from a triangle mesh goes all the way back to when I was attempting to finish my collision detector and had to solve one last collision case, hull versus mesh. The ultimate solution I came up with was less than optimal, which was half the reason I decided to skip the actual partial hull when going over the collision detection methods about a year ago, and showed how to resolve the idea of the partial hull. The other half was I knew I would eventually have to solve the problem for real, and decided to wait until the time naturally came. Enter the AI engine. Shortly after finishing study and moving into design for the engine, I decided that the most pressing issue would be getting AI from one location to another. With this in mind, I decided to reach for the navigation mesh technique. I'll save more on this for part 2, however, the primary reason I went with NavMeshes is due to how much area you can cover with a single polygon. From what I read and have now experienced, pathing is an incredibly expensive operation. Due to this, the more we can speed it up the better, and NavMeshes seem to be the best opportunity. Now, my second attempt at an algorithm for generating this polygon began with development of the pathfinding system in Manifest. The idea was this: the traversable region is relatively flat, and the triangles share their vertices with other triangles aside from the boundary vertices. We can then insert each valid triangle one by one and merge shared edges and vertices while maintaining convexity. On paper, it sounded great. Once finished, you have a set of traversable convex polygons. However, in practice, this was the result. For many reasons, this was not going to work. I tried a few more techniques, but ultimately realized the major problem was this: I'm attempting to make convex regions before processing the entire mesh, and as such, am invalidating future merges, which would create cleaner, larger convex pieces. And the solution was very simple: two-pass approach. In the first pass, insert each triangle edge and expand the polygon without creating any convolutions. Once this finishes, you have a set of simple polygon boundaries. In the second pass, simplify the boundaries and decompose them to generate traversable convex regions. And sure enough, this worked. I feel like I've taken enough of your time, so let me get off my soapbox and into the code. We start here, processing each of the triangles one by one. Before inserting the triangle into the navigation mesh, we have to convert it into world space. I will say this caveat now: the algorithm will not work if the input triangles are perfectly flat, and for the life of me, I cannot figure out why. But I will show later in the video there's a way to work around this, because ultimately we need the polygons to be perfectly flat. With that being said, I generate a matrix that transforms the triangle vertices from their voxel space coordinates into world space. And then once we have our world space triangle, we make sure that it's within the traversable tolerance. In this case, I'm checking for mostly upward facing triangles. However, because we will eventually flatten them, I allow some degree of angle and use a tolerance of 0.95. Should all this pass, we then do the triangle insertion. The insertion algorithm itself is fairly tame compared to my previous attempts. We first start by caching each vertex and then iterate over each cached vertex. If the cached vertex currently exists in an active polygon, we cache the polygon index as well as the vertex index on the triangle that was shared. Once we generate the merge codes for each polygon, we begin the process of expanding the polygon boundary. In the cases where the code is 1, 2, or 4, we skip this because the triangle is only attached at one vertex, and attempting to insert this triangle into the existing polygon would create a convolution. In the case where the code is 3, 5, or 6, we merge a shared edge to join the outer region of the input triangle into the existing polygon. To do this, we check what vertices are shared exactly, and we can achieve that by using the merge code. We're going to find the incoming and outgoing edges from the vertex that was not shared. So for example, here if the code was 3, that means that vertices 0 and 1 were shared, and vertex 2 is the expanding vertex in the triangle. The shared edge can essentially be thought of as a clipping plane where the winding order gets reversed. And to fix this, we point the expanding vertex of the new triangle to the existing polygon's outgoing edge. Then we replace the existing polygon's edge, which shares the triangle's vertex that goes towards the expanding vertex. Then finally, we clean up the removed edges in new polygon, and at the end here we update the new polygon to the old polygon because there may be more merges that have to happen, and they'll be wanting to update with this new, they'll be wanting to merge with this new updated polygon. Finally, case 7 is a special case where we have a missing edge. In this case, we're going to completely remove the input triangle and stretch one of the shared existing edges in the polygon to cover the gap. Just like in the merge case, we still want to keep the old outgoing edge, and this edge happens to be easily detectable. Since the input triangle would create a cycle around the 3 vertices in the polygon, we simply check which edge in the polygon has a next edge whose origin does not exist in the input triangle. Once we have the old outgoing edge, we can do some simple edge walking to determine our other edges. Finally, once we have these edges, we'll stretch the old incoming and the old outgoing together and then clean up the input triangles. Also, one thing I forgot to mention is in both of these cases, after we do the update, we also have this avoid invalidation section here. All this does is go through the polygon that is being merged into and updates the various tracking variables. And this is arguably the hardest part of these decal half-edge-esque type data structures. However, that's all there is to it. And once the algorithm runs on your input set, you get something like this. Now, there is one more section to cover for today, but it's very short, and that is the simplification algorithm. Ramer Douglas Peucker, or RDP for short, is a very fast and efficient algorithm that has been covered to death, and I highly recommend watching the Code and Trained work through the problem either on the live stream or the condensed version. But at a high level, the algorithm works like this. Given a polyline, a line with multiple segments, compute a line between the begin and end point. Find the point with the furthest distance. Compute a new line from the begin to this point and from the point to the end, and check each point in between both segments for its distance. If its distance is below some threshold, the point is non-contributing and is removed. Repeat for each highest vertex from split segments until you run out of vertices. The main key to getting RDP to work on a polygon is to run it twice. Forward from A to B, then B to A. Because the polygon is a linked list, this arrangement generates 2 polylines which trace the polygon boundary. And a good choice for finding the begin and end vertex would be to find the support point from the begin vertex in the polygon. There would be conditions where this is not optimal, but adding a threshold for minimum distance could help. Once you have your polylines, call the refine segment function once forward, then once backwards. The RDP function will then ultimately return a set of valid vertices which exist in the final polygon. And just taking a quick look here at the refine segment function, it's basically what I outlined earlier. Walk the polyline and look for the valid vertex outside epsilon. If one is found, simplify until all points lie within epsilon, at which point the segment is refined. One note I want to make is that before you run the refined segment function, add whatever vertex you're starting with into your refined indices list, because you've confirmed this vertex is valid and are refining from that point. Once RDP exits and we have our list of refined indices, walk the polygon again, and for each vertex not found in the list, remove it. If the vertex is found, go ahead and flatten it by converting it back into voxel space, and then reducing the values to their extraction coordinates, and then back into the interpolated scale. This effectively flattens out our vertices and removes any small elevation differences. This point is then transformed back into world space for decomposition. And so now that we have RDP in play, here's the same 3x3 extraction, but at the end, the polygon is being simplified and reduced using RDP. That will be all for today. I hope you were able to take away something from this, or at the very least enjoyed it. As I mentioned at the start, I will be coming back with part 2 to cover the decomposition and pathfinding portions to actually make use of this polygon boundary we've generated. I do anticipate it being a much faster release than this video. The pathfinding algorithm is more or less working, and the decomposition algorithm is actually being debugged at the time of this recording. So thank you very much for your time. Thank you for sticking around, and I hope to see you in the next one.